Saxon Algebra 2, Lesson 84. We have a very brief two-part lesson. The first thing we want to talk about is the degree of an equation. In order to find the degree of an equation, first we look at the degrees of each polynomial in the equation. Okay? How do we find the degrees of a polynomial? Degree it sounds complicated, but it's easy. Let me just write it out and then I'll show you. I always feel bad writing out these long, wordy definitions because I know they don't make any sense. All right, copy that down and then I'll show you what I'm actually talking about. If we just have the plain number 2, we say that that is a 0 degree polynomial because there's no exponent associated with it. We can think of it here. Let's just go on and I'll make sense of it. This is called a first degree polynomial. This is considered a second degree. Now, let's stop and see if we can make a general rule out of this. This is second degree because, look, the sum of the exponents of the variables is 2. Here, look, there's an invisible 1. That's why it's first degree. If you want to, you can imagine this as being 2 times x to the 0 power, because x to the 0 power always equals 1, right? So this disappears, and that's why we didn't even write it there before. So if we just have one variable in the polynomial, then the exponent tells you the degree. Where this gets tricky is if we have more than one variable. Say we have x squared y m p. That's our polynomial in our equation. Remember, polynomial is just like a random name for algebraic chunks. This is not a second degree because we got to count the degrees of each one of these. So we put in the invisible ones in. This we find out is actually a 5th degree. Not to be confused with Fifth Dimension, who was the band back in the 60s that sang that song, Up, Up, and Away, in My Beautiful Balloon. 5th degree, not Fifth Dimension. But if there's more than one letter, we add those all up. That's what this means, the sum of the exponents of the variables. Okay? It's easiest when we only have one variable, because it's just there looking at us. But if we have more than one variable, we have to add them all up. All right? So when we find the degree of the polynomials in our equation, the degree of the equation, let me flip to the next socket. The degree of the equation is the same number as the degree of the biggest polynomial in the equation. So, I don't like John's. I'm going to make up my own. Let's say that's our equation, and we're trying to find the degree of this entire equation. We would look at the degree of each polynomial This one is a second degree. This one is a first degree. This one is a 1, 2, 3, 4th degree. And this one is a 0 degree, right? Because there's no variable over there. So this would be a 4th degree equation. Because of all of its polynomials, the largest one is a 4th degree polynomial, so that makes it a 4th degree equation. You will not hear me talking about this much in the future. This is one of those kind of random, fussy philosophical concepts that we're going to shove in your brain and then move on. And someday a college professor will be talking about that to you, and you'll be like, oh, okay, I kind of remember that. All right, now we're going to talk a little bit about systems of equations and the different kinds of solutions you can come up with. It's part B. We get to draw some pictures in this one. All right, we're going to draw 3 basic pictures. So down the side of your page, draw 3 Cartesian coordinate systems, if you will, please. Okay, the most typical kind of system of equations that we deal with is one where we have 2 lines and they intersect at one nice point. The key features of this is that there's one solution we see intersecting lines, and there's a fancy name for this. We call it a consistent set of equations, and we also say that it's independent. These words will make more sense when we look at the other ones. Okay, so these are the features of our picture, and these are the fancy names we can give it. Now, let's look at the next type of solution you might get, and this one's the hardest one to draw because what I'm really trying to say is that our 2 equations give us the exact same line. I'm drawing it as 2 because I want you to see that they're on top of each other, but in reality, you wouldn't see space in between them, would you? It would be one exact line. And we say this is an infinite number of solutions because every single point on one line equals a solution on the other line. They match up exactly, and it's one line. This we call consistent, just like the first one, but we call this one dependent. Okay? Again, we're going to come back to these words at the end and talk a little bit about what they mean. The third kind of solution you can get is what I like to call the railroad tracks. And in these, there's no solution because the lines are parallel. And we call this inconsistent and independent. All right, so now we have seen these 3 different types of solutions that we might have to a system of equations, and we've learned these fancy words. Now what we're going to do is we're going to take what we learned and try to write a definition for consistent and dependent. So this first one was called consistent. The second one was called consistent. This one was called inconsistent. Consistent means there's at least one shared solution. There's one shared solution. There's an infinite number of shared solutions. So these two are both consistent. This one does not have any solutions, so it is considered inconsistent. So here's our definition of the word consistent. At least one shared solution. Okay? Now this makes a little more sense. There's one shared solution. There's infinite shared solutions. There's no shared solutions. That's why we describe them that way. Now let's look at the word dependent or independent. The first and the last are independent. This middle one is dependent. So we're going to write the definition for what does it mean for it to be dependent. And this is hard to describe because it's so obvious. One equation holds all the solutions to the other equation. And what we mean by that, it's easier to see than to describe in words. Each one of these lines holds all of the other lines' solutions because they're the same line. There really aren't two different lines. It's just one line written two different ways when you see it, right? So they both have all the answers to each other, right? They're the same line, so they hold each other's solutions. That's what makes them dependent. They hold each other's solutions. These lines don't hold each other's solutions, just the one. These lines don't hold any of each other's solutions. So this word independent, independent I think is easier to understand. They mind their own business. They're different lines. These two mind their own business. They're different lines. These guys are just up in each other's business, right? They look like two different lines, but they really just are one and the same. Remember that dependent, remember that a system of dependent equations would look something like this, where I took an equation and I just multiplied it by the same number. Because then if we divide away the 2, we get the same thing back again. Y equals 2x plus 3. These are not really two different equations. They're the same equation, just written in two different forms. That's what makes that dependent system very weird, is that it's not two different lines. It's the same line. And we give the name dependent to that weird quality of this kind of a system. This kind of a system, all right? It's independent, that makes sense. Dependent is just the fact that that's the same line, dude. Okay, that is the end of lesson 84. The only question in the practice is this one. Is the following system of equations considered consistent or inconsistent, dependent or independent? All you have to do is graph it. All right, rearrange it to y equals mx plus b and graph it, and you'll be golden. And look at these notes, right? so that you can remember what everything means. I don't necessarily expect you to memorize consistency and inconsistency, dependency and independency. I do expect you to understand what they mean. So if someone throws those ideas back at you on, say, a placement test, you'll be like, oh, yeah, I sort of remember this, all right? So make sure you understand it, but you can draw the line at memorizing it. Okay, look. We're now done with week 22. I would love to point out to you, amazing students that you are, that we are getting very close, 3 weeks out from the midterm and then spring break. So, coming down the final stretch here, now is the time to make sure that you are catching up on any homework you might be straggling on. Now is the time to rebuild a position of strength, because if you really stay on top of your game these last few weeks, you will not have to do much to study for the midterm. Make sure you know your formulas. Ask me about any questions, any types of problems that are still causing you duress. Now is the time to just amp up your game a little, and then it will save you a ton of time in preparing for the midterm. I always have your best interests at heart, man. I don't want you to spend I want you to understand algebra, but I don't want you to waste any of your precious time on it that you don't need to. So that's why I'm always encouraging the most efficient ways to do things, all right? I don't want this to take any more time in your life than it needs to take. That's where I'm coming from. Yay, thank you. Goodbye.